proof logging for pseudo-Boolean optimization. Please, Wietze, the floor is yours.
Thank you. Yeah, so my name is Wietze Koops. I am from the Mathematical Insights into Algorithms for Optimization group from Lund University and the University of Copenhagen. And I'm going to tell you about proof logging for pseudo-Boolean optimization.
It could work. You might take a break on your slides after you share them. That happened to me as well.
Okay. Great. Modern combinatorial solvers are highly complicated pieces of software, and then they're also sometimes buggy. And testing doesn't help enough. The most successful solution to deal with bugs in combinatorial solvers is to employ proof logging, as we've also heard extensively this morning. And proof logging originated from the SAT community, and from such as DRAT, ALRAT, FRAT, and there was a big success story. And I want to tell you something about why it was a success story. So why was proof logging successful? And I want to give 4 points. So the first is expressivity. Proof logging in SAT solvers can cover the full range of techniques in existing state-of-the-art solvers, with a small asterisk that unfortunately not symmetry breaking, but other than that, it seems to cover almost everything that people have come up with and come up with now. And to do that, you only need to add some simple print statements and maybe a little bit of bookkeeping. So that's great. It's also very efficient. So when you switch on proof logging in your solver, the execution time maybe goes up by at most 10%. So proof logging only costs you 10% in solving time. And also checking the proof is efficient. It takes a little bit longer than the solving, but not more than a factor 10 longer. It is also very simple. So in SAT we just have the root rule and the RAF rule, and that's it. And it's trustworthy, so proofs are fully complete. Every step in the proof is easy to check. We don't need to rely on something external to say to trust that. And we can even make sure that the checker has a formally verified backend to really be fully sure that when the checker says yes, the answer is really yes. So what existing work do we have beyond SAT, and how does that score on these 4 criteria? So if you look at constraint programming, we had some early work that doesn't cover all these constraints. But the bigger problem is that it's not trustworthy, and that this early work just says like, oh, this clause, this constraint follows by all different, and we would have to trust the all different propagator. That doesn't make it trustworthy. There's very big proof logging that is doing much better on all the other criteria, but their efficiency is a problem. We see sometimes that when we switch on proof logging, the solver takes 10 times as long as without proof logging, and checking the proof can take maybe 1,000 times as long as the solving. And so here the efficiency is a problem, but it's scoring well on other aspects. Subgraph solving, again, we have full coverage, but efficiency is a problem. Mixed integer programming, there's the Viper format, which doesn't nearly have full coverage of what MIP solvers can do. And there is some initial work on variable proof logging, which can cover all the 0-1 ILP brief solving techniques, and they will talk about this, but their efficiency is a problem. MaxSat solving, we have variable proof logging, but again, efficiency is a problem. Completely different domain where we don't have variable, but there are various other formats, model counting. There also efficiency is a problem. And SNT solving, well, it's a very broad area, so it's hard to have full coverage, but also efficiency is a problem.
And simplicity, right?
And simplicity, yeah. So that's in SNT solving. That's a choice that is made in their proof format. They have a very broad expressive language, but also they choose to have like hundreds of proof rules. And what I want to say with this slide is mainly there is some proof logging work beyond SAT. Things before VariPB often had the problem that they cannot cover all the techniques. PrB seems to be good at covering all the techniques, but efficiency is a problem. And that I'm going to show in this talk, that we can also have a very PrB-proof logging for a paradigm where efficiency is no longer a problem. So in this talk, I will present efficient PrB-proof logging and checking for pseudo-Boolean optimization, and it covers all the state-of-the-art, all the techniques in the state-of-the-art solver, rounding SAT and SAT for J. And to give you some preview of the numbers, our proof logging overhead is usually below 10%, worst case is 50%, and the checking overhead is usually below a factor 6, with some worst cases to a factor 20. And to the best of our knowledge, this is really the first time we have practically feasible proof logging beyond SAT. So since this is the first talk after lunch, I just want to briefly recap how proof logging works. So before there was proof logging, we had a solver, which was a black box. It took some input and it gave some output. And now we want to take this black box and we want to see what's inside. So we're not going to change how the solver works, but we're just going to add some print statements that make the solver also output a proof. So now we have a proof as the output, but this is going to be a very long proof, so we don't want to read it ourselves. We want a checker that can automatically check this proof. So the checker gets the answer, the input, and the proof, and will say yes or no. So it will say the proof is correct. It will say the proof is incorrect because there's the wrong step here, or maybe it will say like I'm out of memory, so I don't know if it's correct or not. So what am I going to tell you about in this talk? First, I'm going to introduce the field of pseudo-Boolean solving and pseudo-Boolean optimization. Then I'm going to tell you about some proof rules in a very PrB-proof system. I'm going to tell you about some optimization techniques. Then in particular, I'm going to tell you about core guide optimization and how to do proof logging for core guide optimization. Then I'm going to tell you about how we can integrate the linear programming solver into our pseudo-Boolean solver and how to do proof logging for things corresponding to this. Then I'm going to show you some more detailed results, and finally I give some concluding remarks. But first, I will tell you something about pseudo-Boolean solving and optimization. So this is just solving, no proof logging at the moment. So pseudo-Boolean optimization operates on 0-1 interlinear inequalities, or as we like to call them, pseudo-Boolean constraints. This is a sum of coefficients times literals, and we're saying that this sum is larger than some integer a. A literal is a Boolean variable or its negation, and a Boolean variable can take values 0 or 1. And then if we're not just doing pseudo-Boolean solving, but doing pseudo-Boolean optimization, then we also have an objective that we want to minimize. So just for the purpose of explaining things, I always assume that we want to minimize things. If you want to maximize an objective instead, you can minimize its negation. So -1 times the objective. And to give you a flavor of what we can express using pseudo-Boolean constraints, I give some examples. So here's a class x1 or x2 or not x3. We can write it as the pseudo-Boolean inequality x1 plus x2 plus not x3 is at least 1. We also have a cardinality constraint, which is saying that out of the variables x1, x2, and x3, at least 2 are true. And we have a general constraint where we have, well, also some coefficients that are larger than 1, because in cardinality constraint, the defining property is that the coefficients are 1, but the right-hand side might be larger. In the general constraint, we also can have coefficients larger than 1. And then the main paradigm where both SAT solving and pseudo-Boolean solving are based on is conflict-driven search. And to explain conflict-driven search, I first have to explain propagation. So the idea of propagation is that we infer literal values, so maybe that some literal is true, that some literal is false, from a single constraint, and other literal values that we have already figured out in some other way, or maybe we have decided on. So suppose that we decide on that we're going to set x1 to 0. Then we're going to look at this constraint. And now we see that, okay, x1 is not contributing. If x2 would also not be contributing, then I can get at most x3 and x4, which would contribute at most 2. then I cannot satisfy this constraint. So I have to set x2 equal to 1. If I have set x1 to 0, I have to set x2 equal to 1 in order to be able to satisfy this constraint. Otherwise, I definitely falsify this constraint. That means that this constraint propagates x2 is equal to 1. And now conflict-driven search is trying to build a satisfying assignment literal by literal using decisions and propagations. So it's going to decide on something, do propagations until there are no more propagations. Then it's going to decide again, do more propagations. And then maybe at some point, one constraint propagates the literal to true, and the other constraint is trying to propagate this literal to false. Now then actually, this constraint is conflicting. It's falsified by the current assignment, and then we want to find we want to write a new constraint that explains this conflict and add that constraint to the formula. So let me give an example. So we have these three constraints. So first two clauses that says not z or not w, and one that says not y or w. And we have a general constraint that says that 2x plus y plus c is 2. Let's say that our solver says decide x is equal to 0. Then C3, well, we need to have 2, and the only way we can have 2 is that both y and z are contributing 1 if we set x to 0. So C3 propagates y is 1 and z is 1. Then C2 propagates w to 1 because y is not contributing. And then C1 is falsified because we have already set z1 and w to 1, which means that not z and not w are both 0. So we found a conflict, and now we want to do conflict analysis, which means that we learn a new constraint that will inform us why why x0 is a bad decision. And actually, because here we have only one decision, that means that we're going to learn x is equal to 1. So let's do a derivation of this constraint. We start from C1 and C2 and add those two constraints. We write this directly added then, which goes w plus not w is equal to 1. So that's going to cancel and leave us with not y plus not z is at least 1. And now we're going to involve C3. We're going to add these two constraints. Now the not y and the y are combining, the z and the not z are combining. In the end, we get 2x is at least 1. And then we can divide by 2. We get x is at least a half because we know that x is an integer. We actually get that x is at least 1. So this is a derivation of x is at least 1, and this is something that pseudo-Boolean solver could do. So what are the main approaches for pseudo-Boolean solving? There are two main approaches. One is CNF based. It says we have a pseudo-Boolean formula. We somehow translate this formula into CNF by using a lot of new variables, and then we learn a SAT solver that probably also does conflict-driven class learning, but then for classes only. The other alternative is to do native pseudo-Boolean solving, which means that we're going to generalize the conflict-different search from SAT to pseudo-Boolean constraints. And doing proof logging for such approaches, and also explaining how this works, that is the focus of the talk. I won't talk about the CNF-based approach. There are a bunch of new challenges and new techniques for native pseudo-Boolean solving compared to SAT solving. So one of them is efficient propagation. So in SAT, you might be familiar with the two-watch literal scheme. In pseudo-Boolean solving, this is much more complicated. We can do integration with the linear programming solver. And well, when we're doing optimization, then we have to think about how to do the optimization. And one technique is solution improving search, which just says we're going to try to find better and better solutions. I add constraints that say that solution should become better. But there are also other approaches, such as core guided search, which essentially try to go in the other direction and find better lower bounds. These are the main approaches. And then how do we add proof logging for that? Well, so for conflict analysis, as was explained in the morning, in SAT we can just print the clause and check that it follows by reverse unit propagation. If we do pseudo-Boolean conflict analysis, that doesn't work. Constraints that follow from pseudo-Boolean conflict analysis don't necessarily follow from RUP, even if you have pseudo-Boolean propagation. So we have to give an explicit description of the conflict analysis steps, like the derivation I showed a few slides ago. Other techniques pose further challenges like objective rewriting in core guided search and linear programming integration. Specifically, there we will talk about Farkas certificates and about cut generation. And then I wanted you to make it efficient, but that brings its own set of low-level challenges. So one thing that we need to be able to do efficiently is logging unit constraints, which are constraints that x2 is at least 1, or not x3 is at least 1, let's say. So constraints that say that a variable must take some fixed value. Then also, if we have other constraints and we have learned these units, then we want to simplify away variables, well, for which we know its value. Logging and checking solutions can be a problem because maybe the solver finds many solutions and checking all of them can be quite costly. And since we want to use the formally verified backend cake, we also need to optimize that to get that efficient. And also take that into account in how we design the proof logging. So with that said, I will turn to the variable proof system. So we have seen that the variable proof system is based on the cutting place proof system, which means that we can use any input axioms. We can use literal axioms saying that literals are non-negative. We can add two constraints. We can multiply constraints by a positive integer. And we can do a cutting planes division by a positive integer, which means that we round up the coefficients. And I want to say a little bit more about the division rule. So in particular, why is it timed? So when we divide the constraints by c just over the reals, well, then we divide the coefficients by c and we divide the right-hand side by c. And then since the literals are non-negative, if I make the coefficients larger, then I'm only going to make the left-hand side larger. So I can round up the coefficients on the left-hand side. And now I would also want to make the right-hand side larger. And there we are using that, well, the rounded up coefficients are integers, the literals are integers. So the entire left-hand side is an integer. That means that we can also round up the right-hand side to the next integer. And that's really the strength of this rule. And in fact, it is what makes this proof system reason about Boolean values rather than about real values. Because if we look at the other rules, well, adding constraint is valid over the reals. Multiplying constraint is valid over the reals. The literal axioms are valid for all real values in 0, 1. So if I would not have a division rule, then if I would have a real value satisfying assignment to my input constraints, then it's also going to be a real value satisfying assignment to any constraints that I can derive with addition, multiplication, and literal axioms. So I would never be able to prove unsatisfiability. But because I have division, and the division is only valid over the integers, so that if I look at the rule 2x1 is at least 1, if I apply division divisor 2 on that, x1 is at least 1. This is only valid over the integers. Like a half satisfies the 2x1 is at least 1 constraint, but not the x1 is at least 1 constraint. So division is really what gives the proof system its Boolean flavor. So it's really crucial rule. And this also has implications, not just for the proof system, but also if you think about solving, because it means that we can use division to, it's also an important step for the solver. Okay, let's do the conflict analysis example that we just did as a variable derivation. So we name the constraints using labels. This is a nice feature that variable has. So we have the three red constraints on top as constraints C1, C2, and C3. And then we can write this proof tree in our proof log in ASCII format as this line in reverse Polish notation, which says we take the constraint C1 and the constraint C2, we add that, then to that we add the constraint C3, and then we divide by 2. So this is how we can translate such a proof tree into a line that we can write into our proof log. Okay, now we have seen some rules that introduce implied constraints. We also need a rule for deriving non-implied constraints, such as maybe we want to introduce new variables that define a certain concept. This we can do using the redundance-based strengthening rule. So if we have some existing formula f, we want to add a constraint c to it without affecting whether the formula is satisfiable. So I want, if f is satisfiable, I want to make sure that f union c is still satisfiable. And the other way around, that is clear. I can do this if there is a substitution omega, which maps variables to truth values, or so 0 or 1, or to literals, for which if I satisfy the formula f and I don't satisfy the constraint c, then I can derive the constraint and the formula f and the constraint c under this witness omega. And the way to think about this is that the witness, so if we have an assignment which already satisfies c, well then we're clearly happy. If it doesn't satisfy c, then this rule will tell us how we can make a satisfying assignment. Now if we use this rule in the proof, then the implication needs to be efficiently verifiable, which means that, well, I mean, this is a formula, so it's a conjunction of constraints. Each of those constraints should follow either obviously from the premises, or we need to give explicit derivation in our proof log. But we'll see, actually the proof log, the proof checker has gotten quite good at saying that things are obvious. So let's do an example of this. Suppose that we already know this constraint, saying that the sum of x1, x2, and x3 is at least 2. And we want to introduce a variable y3 that says that actually if y3 is true, the sum of these three variables is not just 2, but it is 3. Then I can write that as x1 plus x2 plus x3 is 2 plus y3. Because then if y3 is false, then it says the sum is 2. If y3 is true, it says the sum is 3. And because we know that the sum is at least 2, and no, it's the sum of 3 literals, so it can be at most 3, these are the only sort of options. The sum can either be 2 or 3. So we want to introduce a variable that satisfies this equality. But in our proof system, we can only reason with inequalities. So we have to split this equality into two inequalities, saying that the sum is at most 2 plus y3, and that the sum is at least 2 plus y3. And we're going to introduce these two constraints one by one using this redundance-based strengthening rule. So we start with C1. We want to derive the formula and the constraint under the witness. The y3 is a fresh variable, so I'm going to choose my witness so that it doesn't affect the formula, the variables that I already have. I'm only going to choose it to affect y3. Then the formula f is untouched, because y3 doesn't appear in the formula. And moreover, because I set y3 to 1, if I substitute that into C1, I get that x1 plus x2 plus x3 is at most 3. And that's a trivial constraint. It follows because the literals are each at most 1. So this shows that we can introduce the constraint C1. Then for the constraint C2, we have to be a bit more careful. Because now C1 is already in our formula. So again, we're going to choose the witness to only affect y3. But now we cannot just say like everything else is fine. F is still fine. F is not touched by the witness. But we also have to look at C1. C1 is touched. But I have to constraint not C2. C2 is saying that the sum of the three literals is at least 2 plus y3. If I take its negation, then I'm saying that the sum is at most 1 plus y3. And now since y3 is at most 1, this implies C1 under the substitution, which says that the sum is at most 2. And then finally we have to look at the constraint C2. Well, if I set y3 to 0, it says that the sum is at least 2. This is exactly my constraint D. So now I have done all the proof obligations for the redundance rule, so I can also introduce C2. And now if I want to express this in variable B, actually I just have to write down the constraints C1 and C2 in ASCII format, but I have to take R3 to the left-hand side because all the variables should be on the left-hand side. But other than that, I just say the constraint, I say the witness, and the proof checker is good enough to figure out the justifications. We can also do proof by contradiction, which is just saying, yeah, if I have my formula and I add not C as a premise, I derive contradiction, then I can add the constraint C. And you can see this is a special case of the redundance rule with an empty witness. Let me do an example of this. So we have two constraints, C1 that says that 2t plus x1 plus x2 is at least 2, and the other one saying that 2 not t plus x1 plus x2 is at least 2. And now sort of if t is false, then the first constraint is telling me that x1 plus x2 is at least 2, and the second, if t is true, then the second constraint is telling me that x1 plus x2 is at least 2. So I should be able to derive that x1 plus x2 is at least 2. But to do this in variable B, we're going to use a proof by contradiction. So if we use a proof by contradiction, then we can use the negation of the constraint, saying that the sum of the literals is at most 1. And I'm going to, it's convenient to just work with greater than or equal to inequality, so I'm just going to multiply with -1, and it's actually the same with this constraint. So then I'm going to take C1 and the negation, I'm going to add them, and then I'm going to see that 2t is at least 1. I divide by 2, I get that t is at least 1. And now I can sort of repeat this derivation with the 2 not t constraint. And then in the same way, I'm going to learn that not t is at least 1. But of course, adding this is going to give me a contradiction. And that means that, so the contradiction is in the subproof. That means that actually we're going to add d to our main database of constraints. So here we have this derivation in variable B. So we say we do a proof by contradiction to learn the constraint x1 plus x2 is at least 2. First, we take the constraint C1, add the negation, divide by 2. That's one part. Then we have the constraint C2, we add the negation, divide by 2. That's the other part. And then we add those two constraints to now on our reverse Polish notation stack. And we get our 0 is at least 1. And then the final line is saying we have completed the proof by contradiction, and the contradicting constraint is the previous ID. And also in the poll line, we have this purple -1, which says, which refers to the previous constraint, and that's because this proof by contradiction environment is introducing the negation as a constraint. Okay. We want to do proof logging for both decision and optimization problems. So for decision problems, if it's a satisfiable instance, we just have to provide a solution, and variable B can check it. If we have an unsatisfiable instance, we need to derive 0 is at least 1. Optimization problems are a bit more complicated. We want to provide a solution with some value, which is an upper bound for our minimization problem. And we want to provide a derivation of the inequality that says that the objective is at least some lower bound. And if we have that upper bound and lower bound are equal, then we have proof of optimality. But we can also have partial proofs that say, okay, we can at least achieve this, and you cannot get better than this, but maybe they don't match. So that is how optimizations proofs look in variable B. Now we will talk about some optimization techniques in our solver. And also a bit about how to do proof logging for that. So solution improving search will find solutions with better and better objective values. And when finding a solution with some value v, we can introduce an objective improving constraint, which says that from now on, we're actually only interested in solutions with value at most v minus 1. Because, I mean, we were trying to minimize, so we're not interested in solutions anymore with a higher objective value. And after finding the optimal solution with some value v star, we have the objective improving constraint that says that the objective should now be less than v star minus 1. And then actually we have a contradictory database, so we should be able to derive contradiction. So in proof logging, what we can do is these objective improving constraints, we can get them in the proof log by the sol I rule, which gives the solution and then says, okay, we have this objective improving constraint. And in the final contradiction, well, we can derive from that objective should be at least V star. So its objective is x1 plus 2x2 plus x3. And we find the solution x1 is x3 is 1 and x2 is 0. And well, if we plug it into the objective, then we see the objective value is 2. So we can introduce the objective improving constraint saying its objective as opposed 1. And the sol I rule is how you do this in very PB. So we say x1 and x3 are positive literals, x2 is a negative literal. So this gives the solution and introduce this constraint. Another very crucial technique for optimization is the ability to run decision solver with assumptions. So remember that we're using conflict-driven search to build a satisfying assignment. And instead of starting from the empty assignment, we can also start from some other assignment that we get from something outside the decision solver. So we can run the decision solver with some pre-chosen literal values, and these pre-chosen values we call assumptions. And then we run our decision solver as usual, and then if this says if we remove, what the decision solver can find out is that the assumptions are consistent or inconsistent. If it's consistent, then it means that there exists a solution extending these pre-chosen values. But then we have a solution to our original formula, and we will usually set our assumptions in such a way that this means that we get a better solution. So we find a better solution to our optimization problem. If the assumptions are inconsistent, then we want to learn a constraint, which we call a core constraint, that explains why the assumptions are inconsistent, and then we can guide that. We can use that to guide setting new assumptions. And one particular way to do this is core guide optimization. Core guide optimization makes these assumptions in the most optimistic way. It's saying, I have my objective. It would be great if just all the literals in the objective are 0. Then my objective value is 0, or some constant term that I have. And that's clearly the lowest value I can achieve. So if these assumptions are consistent, then automatically the solution that I find is optimal. That would be great. Well, usually it's going to be inconsistent in the start. And then we're going to derive this core constraint. And we're always going to pre-process this constraint so that the constraint is a cardinality constraint, which means that it's just a sum of literals without coefficients is larger than some right-hand side. And now we are going to do, we're going to make this inequality into an equality. And for that, we are going to introduce new variables yk. And mathematically, how you should think about these variables is that yj is true if this sum is actually equal to, it's at least j. And I need these variables for j between a plus 1 and k, because I know the sum is at least a and at most k. You can do this with verifications, as was explained in the previous talk. That's not how I'm going to do it. I'm instead just going to directly sort of build this constraint as to inequalities. So there are also other solving techniques which would use this, encode this if and only if as a verification. But I'm instead just going to build this constraint directly. I will explain that next slide. And we so when I say build the constraint, just to be clear, in the solver we can just make this constraint directly. We don't worry about how to build it, but it's in the proof log we need to justify that we can introduce variables that satisfy this. That's what I'm going to explain. So now in the solver we have this equality, and we're going to use this equality to cancel the literal with the lowest coefficient from the objective. The literal that's in this sum of k literals. And then actually we're going to have a times the multiplier by which we multiply this equality as a constant term in our rewritten objective, and then we're going to repeat this whole process with the rewritten objective. Okay, so that was a bit complicated. Let me give an example. So here we have our objective x1 plus 2x2 plus 3x3 plus 4x4. First, we're going to assume that all the literals in the objective are 0. So I'm going to assume x1, x2, x3, and x4 to 0. And now suppose that the decision solver says this is inconsistent. Then we obtain a core constraint, which, well, let's say it's this constraint, x2 plus x3 plus x4 is at least 2. And now we introduce a variable y3, such that x2 plus x3 plus x4 is equal to 2 plus y3. And now we're going to use this equality to rewrite the objective. So I've copied the objective from above, but I've already said, okay, I have 2x2, 3x3, 4x4, the lowest coefficient is 2. So I'm going to take out the 2 x2 plus x3 plus x4. I have some remainder, and I'm going to replace that 2 times x2 plus x3 plus x4 with 2 times 2 plus y3. And then if we expand the brackets, we get this rewritten objective. And then the interesting thing is that we have this constant term 4, which shows that the objective is at least 4, because the rest of the terms are non-negative. And now the core guided optimization would continue and say we look at rewritten objective, and now assume that all the literals in the rewritten objective are 0. But instead, we are going to do proof loading for this example. So we know the constraint, and this is what I should say, it's going to be very similar to the example that you've seen before, but just to give you a chance to really understand this example, I'll go over it again. So we have our core that says that x2 plus x3 plus x4 is at least 2. And now I want to introduce this variable y3 that says that actually the sum is equal to 2 plus y3. We split this equality into 2 inequalities. And now we're going to use redundance-based strengthening. So first we want to introduce the constraint C1. We choose our witness to set y3 to 1. F doesn't contain y3, so it's untouched. And the new constraint is trivially satisfied because it's the sum of 3 literals is at most 3. Then we want to introduce also C2, and now we have to be more careful because we also have C1 in the formula. Y3 is set to 0. The formula is untouched. The new constraint, if I set y3 to 0, it says that the sum of the 3 literals is at least 2. So the new constraint follows from D. And the negation of my C2, which says that the sum of the 3 literals is at most 1 plus y3, because y3 is at most 1, this implies that the sum of the literals is at most 2, which is exactly C1 under the witness. And in variable B, I take these constraints and I write them in ASCII format, I write down the witnesses, and the proof logger will actually figure out what I just explained to you. The proof checker, sorry. So variable B and also the formally verified checker, KPB. Okay, some further details. So what are we actually doing with this derivation? We have the original objective and the rewritten objective. And here I've written them so that you can see how I replaced the right-hand side with the left-hand side of the core with the right-hand side of the core constraint. So this inequality x2 plus x3 plus x4 is at least 2 plus y3. This is one of the equalities that we now have in our proof log. If we multiply that by 2, we actually have the inequality that says that the original objective is at least a rewritten objective. Because if I cancel this x1, x3, and 2x4 from both sides of this inequality, well, then it's this inequality. And that means that if the solver shows that the rewritten objective is at least lower bound, well, the solver will believe that this implies that the original objective is at least lower bound. And of course, we should convince also the proof checker that we can do by combining that inequality objective original is at least objective rewritten, and objective rewritten is at least lower bound. The other inequality that says that the sum of the 3 literals is at most 2 plus y3, that I need in the solver. Actually, I added to the decision solver, because that will mean that if I set y3 to 0, which was our next step in our assumptions, this will imply things. So that's why I need both inequalities. So that's core-guided optimization. The next topic I want to talk about is linear programming integration. And for that, I first briefly recap what linear programming relaxation is. The idea of linear programming relaxation is that we have our pseudo-Boolean formula where the variables are supposed to be Boolean. And I'm going to say, actually, no, I'm going to allow you to take any real values in the interval from 0 to 1. And in practice, we can solve these linear programming relaxations quite fast using the simplex algorithm. An important fact about relaxation is that we're essentially removing constraints, namely the constraints that say that the variables have to be Boolean. So if I remove constraints from a minimization problem, then I'm going to get a better or lower optimal value. So that was a very quick recap of LP relaxation. How do we use this in pseudo-Boolean solving? Well, conflict-driven search tries to build a satisfying assignment. And the idea is that we hope that we propagate and then essentially run in a conflict. Or this is how we make progress towards proving a satisfiability. But sometimes a partial assignment may already yield an unsatisfiable subproblem even over the reals. So if I allow all the remaining variables to be real-valued variables, and propagation does not necessarily detect this, but LP solving can. So we just now and then solve the LP relaxation on the formula and the partial assignment that we have so far. And if this problem is infeasible, then we generate a so-called Farkas certificate, which gives us a reason for the infeasibility that we can then use in our conflict-driven search. If the LP relaxation has a optimal integral valued solution, then actually this is also an optimal solution for the subproblem corresponding to this partial assignment. This doesn't happen so often. If we find a fractional solution, then we sort of want to steer the LP away from this fractional solution in future calls. So we want to add constraints to the LP solver that cut away this fractional solution, and such constraints are called cuts in mixed integer programming speak. So now I will show you something about Farkas certificates and then something about cut generation. So how they work in the solver and how to do proof logging for them. If the solver decides to set y equal to 0, then we have these three constraints, C1, C2, and C3. They are infeasible over the reals. So actually we want to conclude that y should be 1. The LP solver can detect this. But one problem is that the LP solver is using floating point arithmetic. So we cannot trust this in an exact solver. And the solution is to ask the LP solver for a Farkas certificate. This is also why we're specifically solving the LP with simplex. Because this will give us a positive linear combination of the constraints and maybe also of some literal actions that proves infeasibility of this subproblem. And then in practice, this Farkas certificate that proves infeasibility for the subproblem is going to imply the constraint that we want to hold that y is at least 1. Yes?
Sorry, I'm not very familiar with IoT. Is the Farkas certificate a possible combination of constraints with real coefficients or with integer coefficients?
This is exactly the next step I'm going to say. So it's a very good question. It's in principle the LP solver will give us real multipliers, but we cannot work with them. So what we're going to do is we're going to multiply them with something large and then round them to integers. And then we can check that the positive linear combination still implies what we want it to imply in exact arithmetic. So if it's infeasible, then we want that even after the rounding, the multipliers were still infeasible over the integers. And that makes sure that we do not rely on a floating point error in our solver. So we can check this. And to do proof logging, well, maybe the LP solver tells us that we should set maybe it gives us multiplier half for C1, multiplier half for C2, multiplier 1 for C3, and also multiplier half for 2 literal axioms. We're going to multiply those to integers, so we can actually a bunch of 1 multipliers and multiplier 2 for C3. And then if we do this computation, then we will see that this will say that 2y is at least 2. We can divide that by 2 to get y is at least 1. And so, I mean, how the LP solver came up with this multiplier is that we don't need to understand. We just need to check that this indeed results in what we want to do. And then we can check it in the solver, and we can also have variably check it. So we take our, again, suppose that we have labeled our constraints, then we can add C1 and C2, then add twice C3 to this. You can add the literal action X4, not X4, the literal action for X2, and divide by 2. Then cut generation. A cut is trying to cut away a rational solution found by the LP solver, and it has to be a constraint that is implied by the input formula. So as an example, we want to minimize the sum x1 plus x2 plus x3 subject to these 3 constraints. And if we solve this to rational optimality, then we see we should set x1, x2, and x3 all to a half. And now if we add these 3 constraints, then we get that 2x1 plus 2x2 plus 2x3 is at least 3. Actually, over the reals, we see that x1 plus x2 plus x3 is at least 3 halves, which shows that this is indeed rationally optimal. And now to derive a cut, we're going to use our division rule. And now remember that this is what allows us to strengthen constraints over the integers to not, and it doesn't follow over the reals. So if we divide this by 2, then x1 plus x2 plus x3 is at least 2. And then again, we can write this in variable b in this way. We also have some more advanced cut generation techniques. This is cut generation with a mixed integer rounding rule. And this is a stronger rule than cutting planes division. And moreover, the reasoning uses integer slack variables which are not supported by variable b. And proof logging instead uses a proof by contradiction. So the mere cut rule is this little scary formula. So I'm just going to explain it using an example. We should think of it as we do cutting planes division with the divisor d, we multiply with a modulo d, and then we see that the coefficients on the left-hand side can actually be a bit smaller in some cases. So if we apply the mere cut with the divisor 5 to this constraint, well, the 10 we divide by 5 and multiply by 2. And the 5 we just multiply by 5 and divide by 5 and multiply by 2. Then the 6, if we would do cutting planes division, we would get 4 as a coefficient, but instead we get 3 as a coefficient in the mere cut.
So I always struggle to understand this, but so what happens here, like division would always multiply by capital A mod D, but the point is AI mod D could sometimes be smaller. Is this what happens? And this
Yes.
is what we're winning.
Yeah. So in that, indeed, the coefficient of the mere cut is smaller if AI modulo D is strictly between 0 and A modulo D. And this, for example, we see with the 6, it's 1 modulo 5, which is between 0 and 2, and also with the x5, it is 1 modulo 5. So that's where we get smaller coefficients in these 2 cases. The exact mechanics of the formula maybe require a whole separate talk to explain. Another interesting thing that's happening in the solver is that to explain the reasoning of the solver in the most natural way, we would introduce integral slack variables in our constraint. Let's say that we have this constraint C1. Instead of saying that the sum is at least 8, I'm saying that there exists a non-negative integer S1, that then if I subtract that from the sum, from the 6x1 plus 5x2 plus 2x3 plus 3x4, then it is equal to 8. So the S1 is sort of counting, saying this is the slack in this constraint. I do something similar for C2. And this, of course, is not something we can do in variable B because it only has Boolean variables. It doesn't have slack variable, integer valued variables. We compute some linear combination, of these two equalities, and we're only going to keep the greater than or equal to part. Then I'm going to apply a meerkat. And now, interestingly, the meerkat also just applies, it's still sound if you have integer valued variables. So we apply also the meerkat, and now we still have this minus S2, and that sort of allows us to recombine this constraint with C2 prime, which is going to subtract that constraint, because it's an equality that's allowed, and then I get a constraint again over my original variables. And this is a meerkat. It's went a bit fast, sorry, I'm almost out of time. Maybe I'm going to skip how to
do this. We started a bit late.
Okay. So we have our two constraints. We can use the and now we're going to use in the proof logging that we already know what the result is of our constraint. So we have our cut, and we're going to use its negation. And then we're going to do a derivation. So first we're going to add the constraint C1. Then we get this constraint.
So you're going to do a proof by contradiction now?
We're going to do a proof by contradiction, yeah. So I'm going to derive contradiction from C1, C2, and not D. Not D is the purple constraint, C1 is the red constraint. I'm going to first add them. Then I'm going to divide this constraint by 3, and this 3 is coming from 5 minus 2. Remember that the divisor was 5 and the multiplier was 2. Now we're going to multiply by 2. This is the multiplier of the meerkat, is 12 mod 5. Then I'm going to add the negation again. And then I'm going to add the constraint C2. And now I have minus x3 is at least my 1. And that is very quickly you can figure out this is a contradicting constraint. If you really want to drive 0 is at least 1, I could add a literal axiom saying that x3 is at least 0, but actually it's not necessary for very quickly to figure out this is a contradiction. So we can express it in very quickly like this. So we write a constraint that we want to derive in ASCII format, and we translate this proof tree again to a polyline where the -1 is the negated constraint that we introduced. Well, the rest of the derivation in writing this way. And it is a bit mysterious because it's completely different from the reasoning that I tried to show on the previous slide. In particular, the constraints where the multiplier is actually the divisor minus the multiplier is not less than so the multiplier of C1 was 1. This is less than 2. That's why we added before the division, and the C4 we have the slack variable. The C2 had multiplier 4. We have the slack variable left afterwards. This is why we added after division and adding the negation again. So, but this turns out to if you do it for full formulas, it all like abstract formulas, it all lines up. And it's a bit mysterious.
Yes. So this works for every case.
This works for every case. Yeah, there is a general algorithm that says I have the multipliers, I have the constraints, how to line this up.
And you're not searching for the proof. So
I'm not searching for the proof. No, it's a completely mechanical procedure. That's again, it's just printing. It's just adding a few print statements, but it's difficult to figure out what those print statements should be.
And that's simulating the meerkat.
They're essentially simulating the meerkat and the reasoning with integral slack variables. Yes. So then I want to show some results. Recall that our goal was to get proof logging overhead below 10%. That is this green line in the plot. You see that quite a few points are actually indeed below this 10% line, especially for the larger solving times. So this is nice. If we look at decision instances only, where we don't have the core guided optimization, then we're below 20% for running times above a second. If we look at optimization instances, we're always worst case below 50%. But again, most of it is below 10%, and it's more or less getting better the longer the solver is running.
Can you say anything about which optimization instances are bad? Like what's happening?
There are two bad cases. The one is an instance where you have a lot of core rewriting, where these variables disappear from the core if you do lazy variable introduction. Because then you need to sort of do this rewriting over and over again, and in principle you can get a quadratic overhead. But it's just that in principle.
Or that you have to back up and do these telescoping things?
Yes,
we actually see this in the proofs?
Yes, in some instances, yes. And the other thing is if we have a large formula with many constraints that we find a lot of solutions, then checking these solutions over and over again can be a big overhead, and even parsing the solutions can be a big overhead. So those are contributing about equally to these large overheads.
But if you only did the telescoping when you actually need this bound for hardness?
That's we already do.
Oh,
that's already one of the optimizations that we did.
Okay. So you're only doing telescoping when you actually need it. So
yes, and then we also save it so that if we need it again for the same thing and it hasn't been invalidated, then of course we reuse it. So already there, this is one of the low-level details where quantum thinking already went into. If we look at proof checking, oh, sorry, what I told about the overheads was for proof checking mainly. I think proof logging overheads is actually more on the solution side, on logging huge amount of solutions. The proof checking overheads, that is about equally for to the cores and solution checking. Sorry. Okay, proof checking overhead for a rounding set. Our goal is to stay below the factor 10 line, and we see that we're almost there. In fact, for decision instances, we are there. The worst case is factor 10. Overall, we're usually below a factor 6, with some worst cases up to factor 20 if we only look at running times of 1 second. And we have a few mem outs, but it's also we're only running with 14 gigabytes of memory, presumably those could be checked with more memory. Okay, we also implemented proof logging in SAT4J. This is the proof logging overhead. We see that there are a bunch of instances with larger overheads, up to 60% between the 1 and 10 second line. Those are, again, where we find large solutions. But other than that, we're actually almost always below the 10% line. And for proof checking, things are looking even better. So we're usually below a factor 2, and our worst case is actually a factor 4 overhead for SAT4J. And the difference between rounding set, where quite a lot of things we're closer to this green line, is that SAT4J supports fewer advanced techniques, which can cause overhead. And also SAT4J is written in Java, which means that for the same reasoning, it's just taking a bit more time on the solver side, whereas of course the checker stays equally fast. So that's the reason why this plot looks better. Then we go to some concluding remarks. So we can also use proof logging to detect inefficiency bugs. So the main purpose of proof logging was to detect soundless bugs. But we can also detect bugs that are inefficient. So you can just do better things. So 2 examples that we detected while implementing proof logging for rounding set is that sometimes the constraint had an unnecessarily large coefficient. We rounded something up, but it could be rounded down. And the solver was using the objective at most v, where v was the best solution we found so far. We could have used objective at most v minus 1. And here, actually, the fact that we have to specify a derivation explicitly of the conflict analysis steps is an advantage, because if we would just claim like, oh, this constraint is implied, then you could not detect this. And in SAT, that's what we're doing with the rub rule. Here we have to do a bit more explicit reasoning, but this can also be an advantage to detect these kind of errors in the solver. So some challenges for efficient proof logging and checking. We really have to pay attention to detail. I skipped many low-level details how to optimize the proof logging and the checking. Getting these right requires an in-depth understanding of both the solver and of variable B. So we need to know what is efficient for variable B, and we also need to then know, okay, maybe variable B needs, for example, hints for our rub statements, like in LRAD proofs in SAT. We don't just need to know that this is good for variable B. We also need to know how to extract these hints efficiently in our solver, so that our proof logging overhead doesn't blow up. So efficient proof logging is not just as simple as adding just a bunch of few simple print statements. We really have to pay attention to details, and improving this would be great, so that we can also get efficient proof logging with less effort. And also, the solver and the proof checker can have different perspectives on the problem. This we mainly encountered in Sat4j, where Sat4j simplifies input constraints while reading them, so it kind of considers them to be the same. But in the proof, they are different because one of them is an input constraint and another one is a derived constraint. So this requires painful bookkeeping, and actually using labels of the constraints, like I also have seen some of them in the presentation, was very helpful to do this bookkeeping. Future work, of course, we want to have even faster proof logging and checking for pseudo-Boolean optimization. So checking solutions is currently a bottleneck. We also want to have efficient support for simplification of constraints, which we now do in quite a roundabout way to make it efficient. We hope that making it native both makes it easier to do and faster. And we had some low-level optimizations. We already did some low-level optimizations in VariaBB and in KQB. Of course, we want to do even more optimizations. And in particular, all the results that I showed, we're still using the old checker. So if you switch to rewrite in Rust, then probably already these results improve considerably. We can do faster. We also would like to do faster proof logging and checking for further paradigms. So as we have already seen in some of the talks, overheads are a problem. Of course, it's going to be harder for subgraph solving and constraint programming because we have this translation step as well from the native language of the problem to pseudo-Boolean. But of course, it would be great if some of these ideas are still useful for these paradigms. And in particular, max-set solving, I hope that this would improve things. Because there, well, the input is really a special case of pseudo-Boolean. So, what is the takeaway message? I have given you a survey of some techniques in pseudo-Boolean optimization and also explanations of how to do proof logging for these techniques. And this led to the first example of practically feasible certified solving beyond SAT. Future directions are further improvements for pseudo-Boolean optimization, both the solving and the certification. And I also want efficient certified solving in other paradigms. And I would like to ask, is this a start of a new area where we can really get practically feasible proof logging beyond SAT? Thank you, and I'm happy to take questions.
Wietze?
It goes back to slide 39.
39. This?
Yeah, so when you say that you have to specify the derivation explicitly, you mean that you have to write the poll line, or
yes,
do you mean another level of style?
Yeah, I mainly meant the poll line, but for example, also the proof by contradiction gives us. I mean, it's sometimes things have to line up nicely for the division, for example, to work out, because when you're using it, something is going to be rounded up instead of rounded down. It's not sort of monotonic. If you start with a stronger constraint, then in the division you also guarantee to derive a stronger constraint, especially if you're a few steps further down the line. And these things are eventually then detected. Whereas if I just say that this is a implied constraint and we have some logic to check that, then yeah, it says, of course, if I only have steps that say this is an implied constraint and at some point I derive a weaker constraint and things are still implied, then that's going to be fine. Whereas here sometimes we have the syntactic things that need to line up for the proofs to work. And then yeah, if it doesn't work out, then that means that there's some bug somewhere. Thanks. Yeah, okay.
So I'm not so familiar with this world of pseudo-Boolean solving and such. So I was wondering why it takes so long to check a proof. Do you have intuition?
Yeah, so one reason is that the solver can have sort of dedicated data structures for all the techniques that it is using. So the solver knows which techniques it's going to use and can really optimize for doing that specific technique. Whereas the checker is agnostic to this and just has to check whatever it's given. And sort of maybe you're going to do something over and over again, which is actually like sort of cached in the solver. So this is one reason. Yeah, another reason is that what we also see is once we get to more advanced techniques, you can often not completely directly do whatever the solver is doing, but we're translating the reasoning a little bit, and sometimes this can also lead to overheads. But we're also seeing what we saw in the SAT4J plot is here the proof logger and the logger and the solver and the reasoning that's in the proof log are more aligned, and here we see that the overheads are lower, and in fact I think that once we switch to the faster checker, most of that will be below the factor 1 line. And then another thing that I need to mention is that we have both the checker and the formally verified checker. So actually, when we're checking, we run in 2 programs sequentially. So that of course also adds sort of a factor 2. And then in formal verification, things are maybe harder to speed up, like very difficult optimizations might not be supported by the formally verified checker, although it's actually doing really well.
Should I ask another question?
Sure.
Yeah. So, yeah, I'm starting to understand something. So, coming from SAT, right, from SAT Koops, one thing you observe there is that if you write all the hints, right, then proof checking is a lot faster than solving, right? Whereas if you don't write them, then it's about the same. And if I understand correctly, in these procedures that you're implementing here for proof logging, you're essentially recording the equivalent of hints, right? You're using all lines, right? So why does it still not match parity of runtime with the solver?
I think that's still partially like very is relying on Python for some things, and it's just slow language.
Right.
That's a very soon we will have much faster checker in Rust. And then also the KML is actually in itself the sort of language where the formally verified checker KQB is written in is actually pretty fast. But also there, for example, once you go to constraint that contains big integers, this is very difficult to optimize. So yeah, I would say that there, and then again, and then we have all advanced techniques where we're doing different things than in solver. So there, yeah, of course we can hope to be linear, but maybe 1-to-1 is just a bit too optimistic.
I mean, one thing you can say, we're using exponentially more powerful reasoning techniques. So compared to SAT. So it's not clear that checking exponentially more powerful reasoning might be slightly more potential.
Yeah, so this is another example that, for example, you have the redundance rule. Like a solver might just know from some theoretical results that this is fine to do, whereas the checker has to do an explicit step. And if you look at the formula, it's doing actually something of the whole database. Of course, in practice, there are all kinds of optimizations that we don't have to check the whole database, but we still have to check that we indeed don't check the whole database. And that's something that the solver is not doing.
So let's thank Wietze again.